Chapter 8, Eigenvalues and Eigenvectors. Again, we start with a vector space V over a scalar field K and a linear operator A going from V into V. A non-zero vector V in V is an eigenvector of A if there exists a scalar lambda with AV equal lambda V. We say that lambda is an eigenvalue of A belonging to V. Geometrically, the geometric interpretation is that lambda is a scalar that allows V and AV to be parallel or to lie on the same line, as scalar multiples of a vector are parallel to that vector. Our classic example, again, is Kn, and A is a square matrix. And so when X is an element of Kn, not 0, X not 0 is an eigenvector of A if there exists a scalar lambda with Ax equal lambda x. I stress that the eigenvectors are not the zero vector, because the zero vector cannot and never will be an eigenvector of any eigenvalue. So they must be non-zero. And so we have theorem 1,1 with our vector space and our linear operator and our scalar lambda. We define V sub lambda, which is going to be called our eigenspace. It's the set of all vectors in V such that AV equals lambda V. This is a subspace of V, but the non-zero vectors in V lambda correspond to all of the eigenvectors of A having lambda as eigenvalue. So the proof is very easy. It follows the two criteria for a subset of V to be a subspace of V. That is, it must be closed under vector addition and scalar multiplication, as you see. V lambda is called the eigenspace of A belonging to lambda. That is, V lambda contains all of the eigenvectors of A that belong to a particular lambda. Now, theorem 1,2 tells us that when we have a set V1 to V sub m of eigenvectors of A with distinct different eigenvalues, lambda 1 through lambda sub m, no two of which are the same, then these eigenvectors must be linearly independent. Linearly independent. The proof is done by induction on M. And so we have to start again, as you know, with a linear combination of the vectors C1, V1 through Cm, Vm equal to the zero vector. And we must show that all the scalars must be zero, by definition, for the vectors to be linearly independent. So the proof is done by induction on M. So you start out checking M equal 1, V1 in V, V1 not 0. One single non-zero vector by itself is linearly independent. So next, assume M is greater than 1 and assume Ci is 0 for M minus 1, then show all Ci's are 0 for M. And so you can see the proof here. You start out first with the linear combination of the V sub I is equal to 0, and then you multiply that by lambda 1. and then you multiply by A, and then you subtract those two equations, and since lambda j minus lambda 1 is not 0 for all the j's running from 2 to m, we conclude then by our induction hypothesis, it's true for m minus 1, that the C2 all the way to Cm must be 0. Hence, C1V1 is also 0, and that necessarily means that C1 is also 0. So that concludes the proof. So whenever you have a set of eigenvectors and they correspond to different eigenvalues, they are linearly independent. Now we remark when the vector space is finite dimensional of dimension n, and when m equals n in the theorem, then v1 through v sub n is a basis of v, called an eigenbasis, a basis of eigenvectors. Very important, the basis of eigenvectors. Alright, so now let v be finite dimensional of dimension n. Let L be a linear operator on v. We say then that the linear mapping L can be diagonalized if v has an eigenbasis with LVI equal lambda I VI. That is, the matrix A representing the linear mapping is the diagonal matrix A having the eigenvalues on the main diagonal and zeros above and below it. We also say that a matrix A is diagonalizable if it's similar to a diagonal matrix. Now, we're going to get that definition in just a moment, but next let us consider again vector space V having dimension n and lambda, a scalar, and linear operator A. Then lambda is an eigenvalue of A if and only if A minus lambda I is not invertible. That is, it does not have an inverse. Now, you can also reverse it and put lambda I minus A, and the same thing still works out. The proof is very easy to follow. The forward direction and the converse direction is very simple. So I will skip over that for the moment. Alright, now let A be a square matrix over scalar field K. The characteristic polynomial, CP for short, of A is the polynomial denoted by P sub A of lambda. P sub A of lambda is the determinant of lambda I minus A. You could also take determinant of A minus lambda I if you wish. It turns out that this determinant is always equal to a polynomial having the format lambda to the power n plus terms of lower degree with leading coefficient 1. Okay, theorem 2-2. Again, if A is a square matrix, a number lambda, a scalar lambda, is an eigenvalue of A if and only if it is a root of the characteristic polynomial. That is, P sub A of lambda is equal to 0. And that proof is very straightforward as well. So I will skip over that. Now, the procedure for finding eigenvalues. Number one, first, we have to find the characteristic polynomial p sub a by taking the determinant of lambda I minus a, or equivalently, taking the determinant of a minus lambda I. Those differ only by a negative sign. 2. Set that characteristic polynomial equal to 0. Solve for the lambdas. That's a problem for college algebra. You have to be careful. And then 3, for each lambda, we form the system, the homogeneous linear system. A minus lambda identity times x equal to the 0 vector, or you could also turn it around if you want to. Lambda I minus a. The reason I do it as a minus lambda I is so that you don't have to change the signs of all of the entries of the matrix A. So a minus lambda I, all you're doing is subtracting lambda off of the main diagonal of A. So for each lambda, we form the homogeneous system, A minus lambda identity x equals 0, and row reduce it to row reduced echelon form, RREF. 4. Find a basis for the solution space corresponding to that lambda. 5. Choose one basis vector to be your eigenvector for that particular lambda. Note, the book does this differently. After step 2, it writes out the system, again, simply as AX equal lambda x, and simply uses substitutions to find the eigenspaces. It works either way. I prefer row reduction most of the time. However, the book's method works better when the eigenvalues are irrational. You can still do row reduction with irrational entries or irrational eigenvalues, but you're only getting decimal approximations. So if you want it to be exact for irrationals, you would have to use the book's method. And especially if you have complex matrices and complex eigenvalues. But I don't plan on doing any of these. Here's an example of finding the eigenvalues and a basis for the eigenspace for a 2 by 2 matrix. Suppose we have the 2 by 2 matrix whose entries are 1, 4, 2, 3. We find the characteristic polynomial p sub a by the determinant of lambda I minus a, or if you wanted to, you could also do determinant of a minus lambda I. So we get the determinant of what you see here. And remember, the determinant of a 2 by 2 matrix is the product of the main diagonal entries minus the product of the off diagonal entries. So we get the product of lambda minus 1, lambda minus 3, minus 8 equals 0. Do the algebra. So you get the factored form. It's a parabola. It's a quadratic equation that factors, thankfully. Hence, this one has rational eigenvalues, whole number eigenvalues. Lambda 1 equals 5, and lambda 2 equals -1. Now, for each lambda, we must find the eigenspace. So first, let's do the first one. Lambda 1 equals 5. So look at a minus lambda identity x equals 0 by substituting 5 for lambda. So let's subtract 5 off the main diagonal of A. So when we do that, we have the matrix you see, negative 4, 4, 2, negative 2, row reduce it to reduced row echelon form, and you notice that the second column, negative 1, 0, is non-elementary. So that means that the variable y is a free variable or a parameter. Say y equals t or s or whatever you want to call it. So y is a parameter t. You notice in the first equation that x equals y, so x is also the same parameter t. So the solution space to V5 is the set of all ordered pairs t comma t, where t is any real number. So I can choose t to be any non-zero real number. The simplest choice is 1. So if I choose t to be 1, then v1 equal 1 comma 1 is a basis for v5. Next, we do the same thing for lambda 2 equal negative 1, and we find the row reduced echelon form. Again, the second column is non-elementary. Y is the parameter t. X is equal to negative 2y, negative 2t. So the eigenspace for negative 1 is negative 2t comma t. So if t is equal to 1, negative 2 comma 1 is a basis for v negative 1. And again, I note that t could be any non-zero number. 1 is the simplest choice. Next, we have a 3 by 3 example, finding the eigenvalues and a basis for eigenspace of a 3 by 3 matrix. So here's the 3 by 3 matrix that you see. We find the characteristic polynomial, and we see there we're looking at the determinant of a 3 by 3 matrix. Now, recall how to find the determinant of higher order matrices. The 2 by 2 case was simple. Now, 3 by 3 case and higher, we have to find those determinants by expansion by cofactors. And we can expand along any row or down any column. The rule of thumb is to use the row or column that has the most zeros in it. So we note that the first column has 2 zeros, so we expand the determinant down the first column. So when we do that, we get lambda minus 2 times the determinant of the 2 by 2 submatrix, which is the product that you see, lambda minus 1, lambda minus 4, minus a negative 2 or plus 2. Do the algebra, and you get a cubic, a third-degree polynomial that conveniently factors as lambda minus 2 squared, actually, times lambda minus 3. So there's only 2 eigenvalues, namely 2 and 3, where 2 has multiplicity 2. Alright, so next we find bases for the eigenspaces of 2 and 3. First, let's find basis for lambda equals 2. Alright, so we're going to subtract 2 off the main diagonal of A, and then row reduce it to reduced row echelon form. And we notice in the row reduced form that our parameter is going to be x. Notice that the first column is 0, 0, 0. The second column is E1. The third column is E2. So the first variable x is the free parameter, call it t. We note that y is 0 and z is 0. And so the solution set for V2 consists of ordered triples t, 0, 0. So if we choose t or x to be 1, then the vector 100 is a basis for V2. Notice that it's one-dimensional. For lambda equal 3, we do the same thing. Subtract 3 off the diagonal. Again, I noticed that in the row-reduced form, that the third column corresponding to z is non-elementary, so that means that z is the free variable or the parameter, call it t. X is negative a half t, y is negative a half t. And so we find, for example, if we let our parameter be negative 2 to get rid of the fractions, you could say that 1, 1, negative 2 is a basis for V3. Now here's a fact. Every non-constant polynomial with complex coefficients has a complex root. Now, the proof to that theorem is, as they say, complex, pun intended. This is the fundamental theorem of algebra, fundamental theorem of college algebra. All right, theorem 2.3. When A is a square matrix over the complex numbers, then A has a non-zero eigenvector corresponding to an eigenvalue in the complex numbers. Okay. Now, theorem 2.4 says when A and B are square matrices, suppose that the inverse of B exists. Then A and B inverse AB have the same characteristic polynomial and the same eigenvalues. We say that the two matrices A and B are similar to one another. This is the definition of similar matrices. Two matrices, A and B, are similar when they have this relationship, A and B inverse AB. And the proof you can see, which is easy to follow. Now, we're going to find in the next video that symmetric matrices are always similar to a diagonal matrix D, where the entries on the diagonal correspond to the eigenvalues of A. That concludes our video.